All right, here we go.
I forgot that time changes in the United States.
Time always changes. We have like 3 times.
All right, guys, let's go ahead and get started. We're gonna do the intro first, and then we'll get more into this as we get more and more advanced. So let's chat a little bit about area under the curve. Specifically, if I have the y-axis in, let's see, in meters per second or feet per second or miles per hour, and we have the x-axis in hours. So let's pretend, let's just make a nice flat horizontal line. Let's say we have a train, because I always think that is the easiest example. So let's say we have a train going 50 miles per hour. And let's say 1, 2, 3. 3. And let's say I want to know what the area under this curve means between 0 and 3. So as you can see at the moment, I just have a rectangle.
What are those lines?
Oh, it's like a shade. These are like shading, like if I'm shading.
You're shading?
So if I wanted the area of this rectangle, it's just width times height. So it's 3 times 50, and I get what? 3 times 50 is 150. And I recognize miles per hour times hours is miles. So if I have a curve like this, and I have my y-axis in, that's a speed, and I have my x-axis, that's a time, the area of the curve is going to give me what? What does this mean, 150? What does the 150 miles mean? You got to put it into context.
No, I really don't know. Like how much travel?
Yeah, how much it traveled. If this is a train that's going 50 miles per hour, 50 miles times 3 is 150, so you just traveled 150 miles. Does that make sense, guys?
Yes. Yeah.
In the 3 hours, that was alluded. Yes, correct. So, if I have a curve that's a squiggly boy, like that, if I find the area under this squiggly guy, is it still going to be distance traveled?
Yes.
Yes, that's all there is to it at the moment. So at the moment, we're not going to talk about the difference between displacement and distance. It's just distance traveled, area under the curve, for a velocity time gap. Cool or not cool? Perfect.
Will it always be finding an area on a specific interval?
As we get more advanced, we're always going to be finding specific areas all the time and exact. But right now, we're just doing approximation.
What graph is this?
Velocity time graph. So here we go. Example 1. A particle starts at x equals 5. So underline that for the moment. And moves along the x-axis. So that means I'm only moving left or right. Left or right. With velocity v of t equals t squared for time t greater than or equal to 0. Using n equals 6 subintervals of equal width, approximate the total distance traveled between 0 and 3. Use LRAM, MRAM, RRAM. Once you find the distance traveled, where's the particle at t equals 3? Okay, so let me tell you what these abbreviations are. You're going to hear them all the time. LRAM means left rectangular approximation method. RRAM, if LRAM stood for left rectangular, what do you think RRAM stands for? Right, and then rectangular. I'm just gonna quote this. Quote means exactly the same words. Right rectangular approximation method. What do you think MRAM stands for? What do you think the M stands for? Middle or mid. Mid rectangular approximation method. Bless you. Yay or nay?
Yay.
All right. I guess we're starting off basic, guys, and I guess some notes to see here real quick. V of t equals t squared. That graph is always above the x-axis, so that means this particle is always moving to the right. So that's just something to note. So I'm going to put note particle is strictly,
Is it just gonna be half of gravel again?
yeah, well, for 0 to, yeah, it's strictly always moving right. When you use the word strictly, that means like that's it. It's definitive. It's only moving right, and that's the only direction you're moving. Does that make sense to everyone, guys? Okay. So according to the last example that we just did, we said that if we find the area under the velocity time curve, that's going to give us distance traveled. Yes or no? Well, that's what we're going to do, guys, because they want to look what they want. They want the total distance traveled. And what do you take a guess? What do you think this n equals 6 means? That I'm going to use 6 rectangles. That's all it means. So here we go. I'm going to use LRAM first. So I'm going to say LRAM. And I'm going to put finding distance traveled using n equals 6. I'm going to draw as best as I can. This is my velocity. This is my time. I'm going to draw t squared. And from what time to what time? 0 all the way to 3. So I'm going to put 3 here. I'm going to say 1's right here. And I'm going to say 2's right there. Now they want me to use 6 rectangles. So that means each rectangle has a width of 0.5. Does that make sense to you guys? No? Since we want 6 rectangles between 0 and 3. Oh. So,
What's the point of using 6 rectangles?
oh, because if I use less rectangles, that's not going to be as good, the approximation. The more rectangles you use, well, we're getting ahead of ourselves. Yeah, but it's going to be cumbersome the more we use. You guys ready? Here we go. Does everyone know how I got the width to be 0.5? Okay, 3 divided by 6 is 0.5. Okay, here's my first rectangle. Because I'm doing LRAM, you start at the leftmost point. So the leftmost point between 0 and 0.5 is 0. So your first rectangle literally is a rectangle that has an area of 0. It's touching the x-axis, or the time axis, if you call that time.
So n is just the number of rectangles.
Correct. Here's the second rectangle, guys. Start at 0.5, go to the curve. There it is. Does everyone see how I got it? Here's the third rectangle. Go to 1, go to the curve, and go to 1.5. Keep going. 1.5 to 2. And I'm just drawing rectangles, guys. 2 to 2.5. And the last one, 2.5 to 3. Are we okay? All right. How do I figure out area of a rectangle? I just do what times what? Yeah, length times width, width times height. So here we go, guys. Look, first rectangle, 0.5. And then that coordinate, the y value is 0. 0 squared is 0. Plus 0.5. And then I'm at 0.5, so 0.5 squared. Does everyone know where I got that 0.5, that's squared? The next one is 0.5 times 1 squared. 0.5 times 1.5 squared. Plus. I'm writing it all out for now, but later on you can write dot dot dot. 0.5 times 2 squared. I got one more. 0.5 times 2.5 squared.
What are we multiplying by 0.5?
Each one of these width is 0.5. This width right here is 0.5. And then the height is dictated by this curve, which is t squared. Because the y value, the height, So let's say, look at this biggest rectangle right here. So this width right here is what? 0.5. But what is the height? Well, the height is dictated by this curve. That y value is 2.5, or the x value is 2.5. 2.5, when I square it, will give me that y value. You see that? So I'm doing 0.5 times whatever that height is. And that curve is t squared. So 2.5 squared will tell me the y value. That makes sense?
You don't do it plus 3 or 3 squared?
No, because I don't have a rectangle where the 3's at. You know what I mean? Then we take our calculators, guys, and it is cumbersome, but don't worry, you're going to have a calculator on this part of the exam when they ask you this, and you just type it in. Literally the same. So, look, can I factor out a 0.5 all the time? Can I factor it out, guys?
Yeah.
So look, factor it out. 0.5, open parenthesis, and I'm just going to type in those numbers, square it. 0 squared plus 0.5 squared plus 1 squared. And I'm not insulting your intelligence. I know that 1 squared is 1, but I'm just putting it in here so you can see. Plus 1.5 squared plus 2 squared plus 2.5 squared. If I did everything correct, which I hope I did, I got 6.875.
Wait, why isn't there a rectangle at 3?
Because I'm going between 0 and 3.
Yeah, but why is 0 there?
What do you mean? Because I start at the leftmost point. So between 0 and 0.5, leftmost point is 0.
What?
All right.
No, I don't get why 3 isn't there.
Because if I put a rectangle at 3, it would go from 3 to 3.5. But I'm only finding the area of the curve between 0 and 3.
I know, why isn't it? Why don't you add 0.5 to times 3 squared?
Because I don't have a rectangle over here. I don't have a rectangle right here like that.
Why don't you?
Because I'm only going between 0 and 3.
Okay.
You know what I mean? Yes.
So my calculation is 6.88. How do I get to not round?
Float. So go to mode, and then it should say float. On mine, it says float, and I don't have anything on mine. It should not say 6.88. I guess I'll look at it right now, miss, to see what's going on with yours. All right. So using LRAM, I got 6.875. And we'll talk about distance in a little bit. There's no units on this one. There should have, but I stole this question verbatim, so there's no units at the moment. That's using LRAM. Yes, miss. Oh, this is just the particle is only moving to the right all the time. But I'm finding area under the velocity distance curve just to tell me the distance that is traveled. So I have moved right about 6.875 if I use LRAM. So, you know what I mean? There's no units on this one, so no units.
The curve was opposite. That's the other way. That's RRAM.
No, well, RRAM, I'm going to use the rightmost point. You're going to see right now. You're going to see right now. All right, guys, real quick. Is this an over approximation or an under approximation from the real distance traveled? It's an under approximation because we haven't gotten all the area under that curve. Does that make sense? All right, so here we go. I'm going to use RRAM now. So I'm going to put RRAM. So notice on the next page, it's all blank. It's a blank page on purpose. We're going to try to use about half the page for the RRAM. Bless you. Draw the velocity time curve again. There's my velocity time curve. Sorry. Man, you guys are bullies. No, I'm kidding, guys. No, we're good. We're good. It's because you are. You are a bully. Miss McLaren, if you're seeing this YouTube video, I did not call her a bully.
Yeah, she did.
All right, here we go. You guys ready? I'm doing which one now? RRAM. Now that means right rectangular approximation. So between the intervals 0 and 0.5, I gotta choose the rightmost point. So between 0 and 0.5, rightmost point. So now it looks like this. There's my first rectangle. Because, okay, so time out, guys. So why is each rectangle 0.5?
Oh, no, I know, because you need 6 rectangles.
3 divided by 6, which give me 0.5. So each rectangle is 0.5.
But I'm saying, isn't the rightmost 0.3?
I'm looking, I have 6 rectangles, and they're all equal width. So between 0 and 0.5,
And I'm saying, why are you looking just between 0 and 0.5?
I could have started between 2.5 and 3, but I like to start left because I like to read stuff left to right. You know what I mean? Between 0.5 and 1, what's the rightmost point? Between 0.5 and 1, what's the rightmost point?
0.5. If we wanted
No,
to
0.5 is the leftmost.
Oh, 1.
1. So start at 1, go down, and then from 1, make a rectangle, horizontal line, go to 0.5 like that.
Wait, why are we going over the line now?
Because I'm doing rightmost. So you do this. My width is 0.5 no matter what. So between 0 and 0.5, it says RRAM, so I start at the rightmost point. Rightmost point, go to the curve, there's my first rectangle. Between 0.5 and 1, rightmost point, start at the curve, rectangle. You see it? All right. Between 1 and 1.5, rightmost point is 1.5. Go down like this. So notice all of them are above the curve. 2. Look, this one goes to 3, Talia. So you're going to like that one. Because that one does go to 3.
I just don't understand. Why couldn't you start at 3 if you...
You can, but, like, okay, how do you read a book? You read it left to right.
Isn't it right for a reason? Right?
Yeah, every single rectangle starts at the rightmost point.
Yeah.
Every single rectangle starts at the rightmost
Can you
point
draw
within the
again?
interval.
Because I'm having trouble drawing.
Why does it matter if you start at the leftmost point and the rightmost point?
Because that's the approximation method. This is called right rectangular approximation method. So on my interval between 0 and 0.5, I start at the rightmost point between this interval. If you want to start between 2.5 and 3, go ahead. Between 2.5 and 3, what's the rightmost number? The 3. That's my first
That would
rectangle.
help me. I want to draw.
I like to start from left to right. So between 0 and 0.5, okay, 0.5, go all the way to the curve, and then go rectangle. So, pass, hit me. No, there's no such thing as a dumb question. Oh, I know what you're like. Why is it called right if you're moving left? It's called rightmost because what point did I choose? I chose the rightmost point on this little interval.
So it's okay.
See, so between 0.5 and 1,
Yeah, the right side.
yeah, I'm choosing the right side.
Did you show us
That it is. It's what's up?
the first one for LRAM?
Uh-huh.
Where did you get 6.875?
I just put it in the calculator.
Pretty much like that.
Yeah, and it should be 6.875. Look, it's up there.
So I got 11.8.
Nah, that's for the. I think that's the rightmost. All right, here we go. Don't worry, I'm gonna. Here we go, guys. I'm gonna find area under this curve again. Area of a rectangle is length times width. So here we go. 0.5. I'm gonna do it in red. 0.5. The first rectangle. I'm looking at this one right here. 1. 0.5 is the width. I'm using the rightmost point to determine the height. So 0.5 squared plus 0.5 times 1 squared. That's for the rectangle 2 here. Plus 0.5 times 1.5 squared. Plus 0.5, 2 squared. 0.
Is this one going to be bigger just because okay.
Yes, it is.
For every area you do, will the right approximation always be bigger?
No, it depends on concavity.
Okay, well,
But if it's a strictly increasing concave up like this, it will.
so we're going to...
Yeah, but you're already getting to advanced. Right now, we're just doing little stuff. What's up, Mata? All right, I can factor out a 0.5. Here we go. It's going to look almost exactly the same.
So an over approximation is always going to be bigger.
This one's going to be an over because it's strictly, it's the area of the rectangles are above the curve. For now, we're not talking about concavity.
So RRAMs are always going to be over 15.
No, not always. I don't. We're getting ahead, just because let's just do it one step at a time. because we don't want to go into making a rule for it yet because it's going to change.
We're gonna do it with other types of graphs.
Yeah, it's going to change though. So
Wait, so for RRAM, you don't put the first one. Yeah. And, and for LRAM, you don't put the last one. Yes.
in this case, but it's going to change. Like, it also has to do with it strictly increasing, strictly decreasing. If it's strictly increasing, RRAM would also be over approximation. So,
But
all right.
she's talking about the last number.
Yeah, in this case. Yeah, in this case. So you're saying like you want to take a shortcut and just do the last one plus plug in the 3. Yeah, that will work. But I'm going to go ahead and show it all. All right, guys, here we go. 0.5 squared, 1 squared, 1.5 squared, 2 squared, 2.5 squared, 3 squared. I got 11.375, which is what you got the last time. So here we go. Did everyone get that? All right, so using LRAM, I'm just going to put using RRAM. Using RRAM, we got that this traveled 11.375. Is this an over approximation or an under approximation? An over approximation because those rectangles are above the curve. Do we see that, guys? So obviously the real number is somewhere in the middle. So now let's use MRAM.
So, just add the 2 and then average it?
Yes, but we're not. Now you're talking trapezoidal rule. Yeah, we're not. You guys are trying to shortcut here. There's no shortcuts, guys.
Add them and then divide.
In this case, it'll work. Okay, MRAM. MRAM is the middle. So what is the middle between? Well, I gotta put 0.5. What is the middle between 0 and 0.5?
1.5.
0.25. So go to the middle. Here's my first rectangle. You should have some above the curve, some below the curve. What is the middle between 0.5 and 1?
0.75.
0.75. You should have a little bit above, a little bit below the curve, your rectangle. Between 1 and 1.5 is 1.25, a little above, a little below. See?
So the letter in front of the RAM dictates the height point.
The letter in front of the RAM. Now the letter in front of the RAM just dictates what method I'm using. The leftmost or rightmost.
Is the highest.
Yeah. So if it's the right touches the graph, the M means the middle, the left means left. Yes. Okay. I'll post it on YouTube as soon as I'm done. I'm recording it. All right. Here we go, guys. I'm going to calculate this one. 0.5. The middle was 0.25. So 0.25 squared plus 0.5. The middle between 0.5 and was 0.75. Bless you. 0.75 squared. The middle between 1 and 1.5 was 1.25. 1.25 squared. Width times height, width times height, width times height. We're approximating.
Is this taking area of graphs?
Yes. Oh, why do we need to know this? You'll see. Because we're going to be approximating distance traveled. Oh, I'm going to show you one right now. It's going to be really cool. You're going to like it. For those, no, you are. You're going to love it. Because I love it. No, it's going to be awesome. There it is, guys. I want you to notice that the difference between, look at this, 0.25, 0.75, 1.25, 1.75, 2.25, 2.75. The difference is 0.5 in all of them. I want you to notice and observe that. Cool or not cool? All right, I'm going to factor out the 0.5 again, like I've been doing all this time. I'm going to go 0.25 squared. Come on, buddy. Plus 0.75 squared. Plus 1.25 squared. Plus 1.75 squared. Plus 2.25 squared. Plus 2.75 squared. All right. Here we go, guys. Focus, focus, focus. Which one do you think is the best approximation?
MRAM.
What do you think the real value is?
That one?
The real distance traveled.
8.94.
You think it's 8.94? Well, let's find out. I don't know. That's what I'm asking. 9? You think it's 9? All right. Go to the next page. Yeah, relax.
Are you thinking?
That way we don't have to do it over and over again. The AP exam
Oh, wow.
will, if they give you a calculator, I think they will ask you no more than 12 by hand. Last year there was a trapezoidal question, right? How many did they ask? You remember? Like 6 of them? So there wasn't the calculator section, right? I don't remember how many, guys. If they ask you to calculate a whole bunch of them, you're gonna have a calculator. If they ask you to calculate 2 or 3 or 4, it's probably gonna be with no calculator, and those numbers are gonna be nice. Does that make sense, guys? All right, check it out. I want you guys to observe here. This is LRAM. When we use 6 rectangles, did we get 6.875? When we use MRAM, did we get 8.9375? Yeah, look, there it is. When we use RRAM, did we get 11.375? Look what happens if I use more and more rectangles. Does my area get more and more precise?
Yes.
What do you think all 3 of these are converging to?
8.95.
8.95?
9, John.
All right, here's the question, and this is the big deal that's going to lead up into integration later on. As n approaches infinity, do all of these converge to 9?
Yes.
Yes. Does that make sense to you guys?
Yes.
So that means if I put an infinite number of rectangles, that's called Raymond sums, after the mathematician Raymond, all these are going to converge to 9, and that's going to be our next step. We're not doing that yet because we're not advanced yet. Cool or not cool? Yeah, limits are all over the place.
Really?
All right.
Are you serious?
We haven't answered the second part of the question. So look, here we go. I'm going to put it here in the bottom. Distance traveled is 9 units. Write that down, guys. Distance traveled is 9 units. But they didn't want to know. They asked that question, and what other question did they ask?
Where is the particle at t equals 3?
Okay. Look, guys, here's a big deal. Later, Ms. Cortez. Here's a big deal. Where did I start at initially? 5. And you move, the distance traveled is 9 units. So if you move 9 units to the right, what's my new position? 14. Does that make sense?
We were never even at 5.
Yeah, it says right here. A particle starts at x equals 5. So, you're going to write this. Particle at t equals 3 seconds is at x equals, what do we say? 14? 14, period. How are we feeling, guys? Okay, where did I lose you?
X equals 5.
That's my position. Remember that right here, I put it right. I'm only moving left or right. I'm moving on an x-axis, either left or right. So initially, I'm at position 5, and I'm always moving to the right.
When t equals 0, you're at x equals 5.
Yes. And at t equals 3, I'm at x equals 14, because I moved 9 units to the right.
Yeah.
Okay, good. All right, here we go, guys.
Wait, how did you move 9 units?
We found the distance under the curve. The area under the curve. Example 2. Here we go, guys.
That's all you do, you just add it.
Yeah. Because that's the distance traveled. All right, here we go. If f is positive, continuous, increasing function on a to b, then LRAM gives an area estimate that is less than the true area under the curve. So look, positive, continuous, increasing. So here it is, two situations, both increasing. Increasing, increasing. One's concave up, one's concave down. Will an LRAM always give you an under approximation? No, you were right. Yes. Do we see what's going on, guys? So, yes, this is true. Yes. If f is positive, continuous, and increasing, comma, LRAM will always be an underestimate. Will always be an underestimate since rectangles are below curve. Perfect.
What if it's not continuous?
It has to be continuous.
What if there's like a removable hole?
They're not going to do that to you.
Well, what if they're...
They're not, miss.
No, but I'm just saying, just in general, like what would happen?
Well, then, because we got to think of a realistic situation, right? What's up, Ms. Schmidt?
No, I just couldn't read what that word was.
Okay, I'm going to read it again. Yes, if f is positive, continuous, and increasing, LRAM will always be an underestimate since rectangles are below curve. Does that make sense, guys? All right, here we go. Don't worry, we're almost done, guys. If an MRAM sum, because you guys, your sleeping schedule is messed up. If an MRAM sum with n equals 4 rectangles of equal width is used to approximate the area enclosed between the x-axis and the graph of y equals 4x minus x squared, the approximation is? All right, so first of all, do we know where this graph crosses the x-axis? No? Oh. Yeah, so it looks something like this, guys. It looks something like that. Yes. Cool or not cool? All right, so now, how many rectangles do they want me to use? 4. It's not to scale, so I'm going to put not to scale. And they want me to use what? LRAM, MRAM, or MRAM? MRAM. So here we go. Ready, guys? All the width of each rectangle is 1. Cool or not cool?
So that means 0.5.
Perfect. So what's the middle between 0 and 1? 0.5. So go to 0.5, to the left, to the right. There should be some above, some below. What's the middle between 1 and 2? There should be some above, some below. What's the middle between 2 and 3? It's not drawn to scale. Between 3 and 4. So there it is. Here's how I'm going to calculate. I have a calculator, guys. I'm going to go 1 times, let's see, what x value did I use? 0.25. So I'm going to write 4 times 0.25 minus 0.25 squared. I'm not going to do all that. Plus 1 times, yeah, that's too cumbersome. Just do it with a calculator. I'm going to put here, calculator. So like this, 1 times f of 0.25.
Where does the 1 come from?
Width times height. The width is 1 for all of them. plus 1 times f of, oh, that's not 0.25, guys. How come you guys didn't correct me?
Yeah, that's
0.5, and then what's this other one here? 1.5? And then plus 1 times f of 2.5 plus 1 times f of 3.5. Do you guys know how to put that in the calculator? Okay, check it out. Look up there, guys. If you want to follow along, go for it. I recommend it because it's a really good skill for the AP exam. Go to y equals. Oh, I have junk in there. Hold on. Let me take this junk out.
And you just say equal to y1 and then
On y1, I'm going to type in 4x minus x squared. Oh, that's not a square. All right, so there it is. 4x minus x squared. Yes, ma'am. Yeah, I don't recommend that one. But I'll do it with that one too, but I don't recommend it. All right, here's my home screen. 1 times f of 0.5. Does everyone agree 1 times f of 0.5 is just f of 0.5? So I'm just going to write that. So here it is. Alpha, no, not alpha. It's second. No, it is alpha. Alpha trace, there it is, y1. Push enter and then open a parenthesis and then put 0.5, close, plus alpha trace y1, open a parenthesis, put 1.5, close, plus, repeat it until you get to 3.5. 1.5, 2.5, close, plus alpha trace 3.5, enter. Come on, buddy. 3.5, close, enter. I got 11. I got a perfect 11. Cool or not cool? All right, we're almost done. Don't worry. I'll be right now, Talia, in case you found it. Okay. All right, this one's no calculator. And they will ask these questions on your AP exam, guys. You'll see them later on. We got to get more experience, of course, before we're there. All right, guys. All right, BC. Let's solve these guys. Yeah. So here we go. Example 4. An LRAM sum with 4 equal subdivisions. Look, pre-cal doesn't go away. 4 equal subdivisions is used to approximate the area under the curve of sine from 0 to pi. What is the approximation? Okay, first, do you know how sine looks like?
Yes.
Sine of 0 is...
1.
No, guys. Oh, man, I failed you. Sine of 0 is 0. I was your pre-cal teacher, guys. Sine of 0 is 0, guys. Sine of pi is...
0.
0 as well. So here's how it looks. Not drawn a scale, but there it is, more or less. At pi over 2, that's the highest.
Yes, that's the which is 1.
And then since they want 4 rectangles, boom, boom. So then that means this is pi over 4. Pi over 4 plus pi over 4 is pi over 2. And then the next one's going to have to be 3 pi over 4. There it is. And what are they doing? LRAM or RRAM or MRAM?
LRAM.
LRAM. So here's the first rectangle in red. Notice it's not a rectangle. It's right on the x-axis. Here's the second one. Don't worry, we're almost done, guys. Here's the third one. And here's the fourth one. The change in x, or the width of each rectangle, is what? Well, pi divided by, how many rectangles are there? By 4. So far, here's what I see. Width times height. So pi over 4 times, what's sine of 0? 0. Plus pi over 4 times, what's sine of pi over 4? Square root of 2 over 2. Plus pi over 4 times, what's sine of pi over 2? Plus pi over 4, and then sine of 3 pi over 4 is? All right, I can factor out a pi over 4. 0 plus square root of 2 over 2 plus 1.
Unless they give you like a specific like equation, you're just gonna do it length times width, right?
Yeah,
Unless
it's a
they
rectangle.
say y is equal to like 3x squared.
Then, well, I still,
Then, yeah, you just plug it in and then multiply.
yeah, to get my height. You know what I mean? All I'm doing is length times width. What's the answer, guys? Is it C? Oh, yeah, it is. How do we feel? Okay. For those of you that are saying, I don't know when I'll ever use this, this is useless, blah, 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 I want you to take 3 minutes to read all this. Don't worry, we're not going to do any more calculations. Take 3 minutes to read the back page, guys, and then we're going to talk about it. Just read it.
What if I trust you?
No, just read it. No, just read it. Mata, trust me, read it.
I don't even have insurance.
All right, guys, read it. Take 2 minutes.
Can you read it?
Yeah, I'm reading it right now. Wow, look at all this. Guys, look how beautiful this math is. Just so if you've ever gone to the doctors and they wanted to check your blood flow, look, this is how they can check how your heart is doing. They inject a dye into it, they look at the concentration level, they put a machine into it, and they calculate the area under that curve to see how much blood is flowing through the aorta. Isn't that amazing? So look, here's calculus in action, guys. Of course, the doctor, trust me, the doctor has done lots and lots of math. As you know, calculus, at one time he did, but now, you know, the computer is doing all this now, right? They put the dye concentration, they put a little catheter or something to measure the concentration. Have your parents ever gone through something like this?
No.
Well, ask them. Look, this is calculus in application, guys. Isn't that cool or not? I think it's really cool. How do we feel? Okay, we have one activity. It's very simple questions. I think some of them are multiple choice. It's over this. With a calculator, you can work in groups, but I want it today. Or try it. Cool or not cool? All right, guys, we're done.